We're going to get a little bit of practice using the current equations and getting an idea of how the devices work by looking at pass transistors. Now this is just a terminology that's been set up that really tells you that we're going to have a MOSFET transistor and we're going to pass the voltage from one terminal to another terminal, and this helps us understand how the voltages are passed from one transistor to another. So what we've got here is an enhancement Nmos. So we've got the enhancement Nmos here, and what we do is we fix two of the terminals. So in this instance we've fixed the gate terminal at 0 volts and we've fixed this terminal here at 5 volts, and we've started off with this side here sitting at 0 volts, and what we have is we have a capacitor at this point. Now don't worry too much if you haven't come across some of these things like a capacitor. I'll explain it as we go along. So what we're interested in here is how this device operates with the 0 volts here, the 5 volts here and the 0 volts here. So the first thing we have to do is we have to determine what is the source and what is the drain. Now it's an enhancement Nmos. It's an Nmos device. Electrons are the majority charge carriers. Electrons travel from a low voltage to a high voltage, and the low voltage side is the source. So this is the low voltage side here. So this must be the source of this transistor. So we can put that in here just now. We'll just make a note of it. So this is going to be the source, and this terminal here is going to be the drain. So the current, conventional current is going to flow in this direction, drain to source, but the actual electron flow, as we know, is from the source to the drain. So let's analyse this little circuit. So we've got the threshold voltage here, Vt, is 1 volt for an enhancement Nmos. We're interested in looking at the VGS minus Vt. So the VGS, well, the V gate to the source, well, the gate is 0, the source is 0, so that's going to be 0 minus 0. And minus the Vt, well, Vt is 1, so we're going to have 0 minus 1 as a value of minus 1. So we can see here that VGS minus Vt is less than 0. So if that's the case, then this device must be cut off. That is, there's no current flowing in this device. So let's see what happens now if we were to maintain the 5 volts here and we changed the gate voltage to 5 volts. And we're interested to work out what's going to happen at this terminal here. So this in effect is the passing of the voltage. We're going to pass a voltage level from one terminal to another terminal. So in this instance, we're going to pass this voltage to this terminal. So what would be happening in terms of the conventional current flow is the current would be flowing in this direction. So as the current flows in this direction, what happens is it charges up this capacitor. That is, the voltage in this capacitor is going to rise, and we're interested to find out what voltage we end up with at this side. So again, we can look through and use the same current equations that we've seen in the opposite here. So we can look at the gate VGS. So again, we've got the drain here and we've got the source at this side here. So the VGS is going to be, well, VG is 5 and the VS, well, we don't know what the VS is, so we'll just call it VS for the moment. So we'll just say 5 minus VS, and we've got VGS minus VT, so it's 5 minus VS minus the VT, which is 1. So we're going to have 4 minus VS. So VGS minus VT is 4 minus VS. Now, we're interested to find out whether it's in cut-off, whether it's in the current is flowing, it's in the saturation, whether it's in the linear current. So we have to compare it with the voltage between the drain and the source. So now here the voltage between the drain and the source is going to be 5 minus the value Vs. So we'll get 5 minus Vs. So we know that it's going to be in cut-off if VGS minus VT is less than or equal to 0. So that's the first thing we can test for, is whether this isn't cut off. So what we can say is VGS minus VT is the 4 minus VS. So 4 minus VS is less than or equal to 0, then we know it's in cut off. So we'll just transpose this equation. So minus VS is less than or equal to minus 4. So VS must be greater than or equal to 4. Now just be careful with your greater than and less than signs here, because whenever you multiply throughout this inequality via a minus 1, you change the sign, so it goes changes from less than equal to greater than or equal to. So if this voltage here at this side rises above 4 volts, then the device cuts off and no more current flows. So that's what we've got noted here. So it's cut off if the VS is greater than or equal to 4 volts. So what are the other two options? Well, we could be in a current could be flowing, and we could be in the linear region, or we could be in the saturation region. So let's check for the linear region. Well, we'll be in the linear region if VGS minus VT is greater than VDS. So just remember your current equations here. So in this instance here, the VGS minus VT is 4 minus VS, and the VDS is 5 minus VS. So I've put a big cross here because, well, this is not possible, is it? We can't say 4 minus VS is going to be greater than or equal to 5 minus VS. Simply put a number in, say VS is the number 1, then maybe 4 minus 1, which would be 3, and we'd be saying 3 is greater than 5 minus 1, which is 4. So we'd be saying 3 is greater than or equal to 4, and that's patently absurd. So it can't be in the linear region. So then we can check and say, is it in the saturation region? Well, it's in the saturation region if 4 minus VS is less than or equal to 5 minus VS, and that's more like it. Put a value in for VS, say 1, so 4 minus 1 is 3, so 3 would be less than 5 minus 1, which is 4. So that's possible, it could be in the saturation region. So what happens then is the device is actually in the saturation region, and this is the saturation current that's going to flow. It's going to be a beta n upon 2 times our 4 minus Vs all squared. So this is just the saturation current equation we've seen in a previous video. So what's this really telling us then? Well, it's telling us that this device is going to charge up at this side. The capacitor is going to charge up, and it's going to charge all the way up to 4 volts. But whenever it reaches 4 volts, this device turns off. So it means that whenever it passes this 5 volts across to the other side, it doesn't pass the full 5 volts. We only get 4 volts at this side. And this is the summary here. The capacitor is going to charge up to 4 volts, but then it's going to be cut off. So this voltage drop here is called the threshold voltage drop, when we pass the voltage from one terminal to another using this little pass transistor. So take your time and read over that and try and understand it. But what we'll do now is we'll go on and we'll look at the simulation, and we'll recreate what we've got here in our simulation file, and it'll all become quite clear what's happening. So you can open up the file in the resources section. So this is the same file we've been using in order to simulate our device. Now we're interested in an Nmos enhancement. So the Nmos enhancement has got a threshold voltage of plus 1 volt. So VT is already set here at 1 volt. Okay, so there it's VT is at 1 volt. We can just leave the width and length ratio as 10 upon 2. Now let's have a look and see what's happening here with the voltages. We're going to start off with the gate at 0 volts and the drain at 5 volts and the source at 0 volts. So this is the same as we've seen just in the example that we looked at just a second ago. So the gate and the source are sitting at 0 volts and the drain is sitting at 5 volts. So the current's going to flow down this direction. That's a conventional current flow, and if we were to draw it in here, we would have a little capacitor sitting in here, and it'd just be charging up that capacitor, and that would be increasing the voltage in the source side. So you can see right away that as soon as we put those values in, we can see that the device is switched off, and you can see it's in cut off here. There's no current flowing in this device, and you can see why that is, because there's no inversion layer. The line is away up here, okay, so it would have to be down below within the channel here in order for there to be an inversion layer. So this device is cut off. Now what we were going to do is we're going to increase the gate voltage from 0 volts up to 5 volts. So this is the second part of our problem that we were working on. So let's increase this up to 5 volts. So you can see as we increase this up towards 5 volts, we're going to get into a saturation current. So we're in the saturation current now, which is the red section here. So you can see it's saturated, and this is a current that's flowing. So we can increase this here all the way up to 5 volts. Now whenever we get up to 5 volts here, we've got the maximum saturation current that we're going to get, and you can see here there's a pinch off at this point, so the current's flowing, the electrons flowing down in this direction and out here, but the actual conventional current flow is from the drain to the source, so it's going from this side to that side. So the current's flowing down through this device here at the moment. Now after a short passage of time, what would happen is the capacitor is going to charge up, and as the capacitor charges up, it means that the source here is going to increase. So the voltage on the source is going to start increasing. So there's the voltage on the source here, so we'll start increasing it. Now we've said that it's only actually going to go up to 4 volts, and you can see that that's the case, because look at what's happening here. As we increase the voltage on this source, you can see that the inversion layer is now decreasing, and at a point where it gets to 4 volts, say it's 3.5, so at 4 volts exactly, then you can see that there is no inversion layer here. So now the device again is cut off. So it means that we're going to get up to 4 volts here on the source, and then that device is going to get cut off. So that means that by charging up that capacitor, we've passed on the drain voltage to the source, but we've dropped a threshold voltage of 1 volt. So that will become important later on whenever we look at other circuits and some circuit designs. So let's move on, and we'll do the same with another example.